Now, why did it matter that I qualified that statement by saying that it is homogeneous in its reference configuration? Not difficult to think why, right? Because I may start out with this body completely homogeneous in the reference configuration, but I'm deforming it, or well, I could do this, right? I could take this and deform it so that I'm really compressing it now. As you may imagine, since I'm not compressing it quite uniformly, I'm probably compressing it more near where my hands are. One would expect that in the deformed state, the mass density is no longer homogeneous. Okay? So what we're seeing is that the mass density of the reference configuration is one thing, but that can be changed by the deformation. All right? So we need to have a description for that, right? A mathematical description. Okay? That's not at all difficult. Okay. And here's how we get to it. Note, first of all, that we can think of rho 0 of x as a limiting process. Okay? So we can think of it as the limit as the volume of some neighborhood of the point x goes to 0. Okay? In this limit, what we want to consider is what I will write as the mass of that neighborhood of the point x divided by the volume of that neighborhood of the point x. Okay? So, in the reference configuration, what we're talking of doing is, right, we have a point x. I'm going to draw a rather large neighborhood of it just to make our arguments. Okay? That neighborhood is n of x. Okay? So rho 0 of x is that limit. Okay? We're talking of that volume going to 0 and what happens to the mass, right? So it's that ratio. Okay. But you observe that this sort of thing immediately makes clear to us how to think about the mass density post deformation, right? So under the deformation, right, we have omega sub t. We have that point little x, right? And let me say that, right, obviously draw the neighborhood as being bigger. I'm going to use the same symbol. Well, no, maybe I should use a different symbol. So I'm going to use that script little n about little x as the neighborhood in the deformed configuration. Okay? So now we know, of course, from this that if we now write out the mass density in the deformed configuration, we're going to write it as parameterized by little x because it lives on the deformed, the spatial configuration. We also know now that it can be a function of time, right? I'm not going to put a naught on this because it's the current or the deformed density, right? This now, using the same idea of the limit process, is just limit of the volume of the neighborhood now script little n of little x. Now, mass of that neighborhood of little x divided by the volume, right? Oh. Sorry, the neighborhood is not a it's not a vector or tensor. Okay, just right. Okay. Now the mass of the two neighborhoods remains the same, right? That's what we're thinking of. We're thinking about the same set of particles going from capital N to little n, right? Okay, it's the same neighborhood whose deformation we're following. So the mass remains the same, right? So this is then limit as the volume of n little x. Okay. Now we can write this as the mass of the original neighborhood, capital X, divided by the volume of the original neighborhood, okay, times the ratio of the volumes of the neighborhoods. Okay? All right? Now, remember that the limit of the volume, limit of a product is the product of the limits, right? So we see that now, I'm not going to go through all of that process, but we see that now when we take this limit, sorry, I need to specify that this volume is going to 0. Forgot to write that limit there. Okay. Now, the limit of a product is a product of the limits, and from the first term in that limit, we know that we get back rho 0 of x. Okay? What do we get back from the second term in that product? Think about it for a second or more. It's the ratio of the original volume to the deformed volume. When we study the deformation gradient and its properties, we observe that that ratio is essentially determinant of f, right, the whole to the minus 1. Okay? So what we observe is that rho of little x, function of time, is rho 0, function of position only, times determinant of f, which brings in the time dependence. Okay, let me see. Okay, now, just for the sake of brevity in writing, it's common for us to write the determinant of f as j. Okay? So, what we have is that rho, function of little x, and time equals rho 0, function of position, j, function of reference position and time. And of course, in this, we have that little x is phi of capital X and time. Okay? So this gives us now the relation between the mass density in the deformed configuration and the mass density in the reference configuration.